In 2003, a heavy storm swept through the Swiss Alps. A single pine tree fell, snapping a high-voltage power line. Within minutes, 50 million people across Italy found themselves completely in the dark. The damage extended far beyond the power grid. Internet servers went offline, and entire train systems ground to a sudden halt. Understanding how a snapped wire in a Swiss forest can crash computer servers in Rome reveals the hidden vulnerabilities that now define our everyday lives. Engineers map infrastructure as a flat grid of dots and lines. We treated systems as completely separate. The power grid was one map, the internet another. In isolated maps, if a dot fails, neighbors absorb the weight, keeping the system stable. If we rely on those isolated maps, an electrical problem in Switzerland causing a widespread internet failure in Italy shouldn't happen. It means our standard models were missing the links between the systems themselves. To see our infrastructure accurately, we layer those separate network maps on top of each other. Within a layer, horizontal lines are standard connections, but between layers, invisible vertical lines are direct lifelines, where an internet router physically requires electricity from the power layer below. You see this lifeline in the real world. A high-voltage station relies on the nearby telecom dish to monitor safety and control electricity. Tying our systems together vertically makes them incredibly fast and efficient, but it creates a path for a failure to jump into another system. A broken power line shuts down a power station. That failure travels up the vertical lifeline, killing the internet center above it. Without internet, power stations go blind and shut off. This ping-pong effect bounces damage back and forth between networks, accelerating faster and faster. Instead of fading out slowly like an isolated grid, an interdependent system experiences an abrupt collapse. In the physical world, this abstract math translates into transit terminals full of stranded passengers and cities completely cut off from basic logistics. These complex, layered networks hide their true fragility. They operate with perfect efficiency right up until the exact second they stop completely. Once this ping-pong effect starts, how do engineers actually step in and stop it? This diagram illustrates a strategy physicists call healing. As the cascade is happening, the system dynamically builds new horizontal connections around the failed area to bypass the damage. Another approach is islanding. Engineers intentionally sever connections to create a firebreak, sacrificing a small piece of the network to isolate the problem. By cutting those lifelines, they temporarily turn an interdependent system back into an isolated one, which forces the ping-pong effect to stop. It is a strange reality. Sometimes the most effective way to save a highly interconnected world is to intentionally break its connections. But the best strategy is prevention, through a concept called autonomy. If we install independent backup batteries on an internet routing center, it no longer needs that vertical lifeline to the power grid. When the power goes out, the local battery kicks in, and the failure is trapped. It cannot jump networks. Equipping every location with its own power source is expensive and less efficient than just relying on the main grid. Engineers have to carefully balance cost and safety. Extreme connection is exactly what makes modern civilization possible, but a strategic amount of independence is what keeps the lights on when the dominoes start to fall.